Hey everyone, this is Jane, an aspiring AI engineer with hands-on experience as a NLP researcher and generative AI engineer at different startups. Today, we will explore the soft margin SVM and I will break down the core mathematical concepts, and at the end, we will uncover how these equations bring intelligence to SVM. Understanding math is not just theory, it is the key to develop critical and creative thinking which the industry values deeply in this age of AI. I am super excited to guide you in this AI journey, and let's get started. Let's dive in, guys. First, why we need soft margin SVM? To know that, let's understand. I will give you the brief introduction of hard margin, and to get a clear-cut idea, I already uploaded 3 videos of half an hour length. You go and watch them. You get very clear clarity, and come here. But I will use enough information about hard margin to understand soft margin. Right now, let's take a data set, guys. We know CGPA and IQ of different students, and the blue points indicate here, as you can see my cursor, who are placed and these are not placed, and we could clearly find a mathematical formulations like a line that could separate this data, right? Then SVM says, hey Jane, I am there, I will help you to find the model which is robust. Okay, SVM, how is that? Please help me. Okay, it says, think about the margin that it has with respect to the positive and negative class. Okay, what is margin? SVM? It says that it is the distance from your point of positive class, the closest distance of your positive class point to your negative class. You can clearly see here the margin I defined here. You can see this is the positive negative class closest point to your hyperplane. M2 is your hyperplane, and this is the positive class, and this is the closest point to your hyperplane. This is the margin, right? And here I selected 2 models here. Which one is better? Think about it. You can clearly see M1 is better. But how can we find this SVM? Please tell me. Okay, it says first find this margin for a general line. Take a line here, general line, and just we consider a hyperplane in general. I have written the hyperplane equation like this. You can see why these are like this. You please go through the videos that I already uploaded and you get clear clarity. Right now, it's the same thing, right? The same thing, yeah. All these points, pi minus is the negative marginal plane because all the negative points would lie to the left or on this line. Pi plus we are considering as a marginal plane, positive marginal plane, where the points lie on this or to the right. No point would lie in between the margin. That is very hard to digest, right? That's what hard margin does. It tells that no point should be there in the margin. No point should be there. And how would we know whether it is left side to your negative margin or right side to your positive margin? These are the equations, right? I already explained in those videos. And now we uniform a equation for these two. Let's uniform. See, this is one constraint, right? All the negative points should be below or left side to the pi minus, right, and all the positive points should be right side to this pi plus. But let's uniform that, guys, because we know the label. As you can see, yi is +1 here. You can see my laser cursor, right? And clearly, yeah, I could able to uniform it because I already explained. Yi is +1 means you get this first constraint. If yi is negative means you get the second constraint. Hope this is clear. Now let's find the distance between the 2 parallel lines pi minus and pi plus. I hope you know the distance. If ax plus by plus c1 equal to 0 and ax plus by plus c2 equal to 0 are 2 lines, then what is the parallel distance? c1 minus c2 by root of a square plus b square, right? Simple. That's what we do here. We do that. I did not written the calculation because I already explained those videos, and here the margin we end up 2 by norm of w. What is norm? Under root of a square plus b square, guys. That's it. Because this is a general one. It's for n dimensional. Under root of a square is a 2D line, right? Now it is for hyperplane. W different for hyperplane for n dimensional data, right? Now we got a constraint. Now what is the goal of SVM? Please listen carefully. The goal of SVM is to find the robust maximum margin line, right? Now we want to maximize the margin, but we ended up with a constraint as well. This is a constraint. Now let's understand why hard margin is not used in the real world, because as you can clearly see, you cannot find data like this in real world, right? No, you cannot find. The person having less CGPA could not be placed. A person having high CGPA could not be placed having less IQ also. If he has more IQ but less CGPA, but he could be placed, right? This data could not be like this. Some points would mix with this negative class and some point would mix with the positive class, right, guys? Now but let's understand what if a point, why it is hard margin. I hope you understood, because all the points should be this side, all the negative points should be this side, right? All the negative points, but some points would also be this side. Means there is a problem with this constraint. If we somehow soften this constraint for the points that present in the margin, for the points that are misclassified only little bit misclassified, that is fine. Some misclassification, yeah, some error would be fine, right? But what, guys, this constraint, what it will do, it is says very strict. Okay, we understood that, yeah, we have to soften this constraint, right? How can we do that? Now literature helps us with the slack variable, and with this slack variable we can clearly understand any point that could be satisfy this constraint. Okay, this is how slack variable is defined, guys. This is how we slack variable is defined. 0, 1, maximum of 1, 0, 1 minus yi is your label, w transpose dot xi plus b. This is the equation of the plane, right? If the maximum value is your slack variable. Now let's see whether it is correctly classified. Point, this is correctly classified, right? This is your margin, and all the points left to this are negative points, negative class, and this is also negative. Yes, okay, correctly, but it is present inside the margin, right? But the constraint should be satisfied. Now the constraint is modified like this. Let's see whether this modified constraint will be softened for this point or not. Yeah, let's find zeta. Zeta is maximum of 0, 1, minus yi is minus 1 this point because it's negative class, right? And minus 0.5. I assumed that since this is 0, pi, black line, our hyperplane is w transpose dot x plus b equal to 0. I assumed as this as minus 0.5. Approximately, guys. Approximately. I hope I'm clear. If you have any doubts, write in the comment section now itself. Right? You have to understand very clearly. I'm going very slowly, I think so. You just understand, stop the video, pause the video and understand. Right? Now I found the zeta for this point which is present in the margin, inside the margin, and you could see 0, 0.5 maximum. Okay, 0.5 I got. Okay, inside the margin 0.5. Let's see whether constraint is softened or not, right? The modified constraint. Oh, pi is minus 1, that I know, and this is 0.5 because w transpose dot x plus b is 0.5. I approximately thought, yeah, this would be on minus 0.5 line, and greater than 1 minus 0.5. Yeah. Oh, cool. Yes, it is softened. Okay, let's see for different points. See, let's say now this is the point, right? This is misclassified. Whether it is softened or not. Let's see. Now zeta, this is our mathematical formulation of zeta. And let's see for this point, okay, 0, 1 minus yi is again minus 1, that we know, and w transpose dot xi plus b. I assume this as 3. Since this line, this green line is 1. This green line is plus 1. I assumed approximately as 3, guys. I hope you understood. And yeah, I ended up with 4. Okay, for wrongly classified points, if you find zeta, it is coming greater than 0. Okay, I got a conclusion from here. And let me see whether the constraint is softened, the modified one is softened for this or not. Let me see, guys. Minus 0.5. Yeah, cool. This is very cool. Correctly classified blue point. Yes, gamma, yeah. Now I took a point that is correctly classified. This I took the blue point. This is correctly classified, right? Because this is on the margin. This is a support vector, right? This is correctly classified, and I found okay 1 minus 1. I hope you understood how to calculate zeta, and we ended up with 0. Okay, for correctly classified, okay, 0 is coming, and yes, it is softened. Yes, it is softened. Okay, let's write the conclusions now. Oh, zeta 0 for correctly classified. Zeta would be minus 1 for those points that present in between the margin, and zeta greater than 0 for misclassified points. Okay, zeta greater than 0 for misclassified points. Now question that got to my mind is that whether is it a constraint now? No, right? It is satisfying for every point, whether it is misclassified or not. No, it should not. It should not accept too many misclassified points. It is accepting if some point is present in at the laser pointer that I pointed, that also it would be satisfied. No, those are totally misclassified. Those points that are present near to the green line could be misclassified. Yeah, those are fine. I can accept those misclassifications, but I cannot accept at the end at the two right side. Right? No, I cannot accept those. Means if I take a larger value of zeta, then misclassifications are more, right? These misclassifications are more. Then it is not at all a constraint, but I need a constraint definitely, right? I need a constraint definitely, because all the positive points should be greater than this, negative points should be greater than this, and some points could be misclassified a little bit and could be present inside the margin. That is fine. But how can we do that? How can we how can we change, how can we maximize this, how can we minimize this zeta, right? We want to minimize this zeta. I hope you understood why we want to make, because we want to reduce the misclassifications. I hope I am clear, guys. I hope I am clear. Now let's see, we want to minimize, that we understood. Okay, now see, you only see my cursor, forget about everything. See, my cursor is at the summation 1 to m zeta, means all the zeta. For every data point we are defining zeta I, right? Yes. Now we want to minimize. SVM says we have to minimize. Okay, SVM, I will do that. Yeah, I am doing minimize. What is this then? You might be wondering. Guys, this is our margin. Before we saw, right? Before we saw in the hard margin, same margin would be coming. Whether it is soft or hard, you calculate that. Definitely. This is the margin. But I reciprocate it for minimization, right? We want to maximize this. Now reciprocal of this, norm by 2. Now I want to minimize that, right? I have to minimize that, right? I took the norm square, because norm square is nothing but inner product, like a dot product. That's why I took the norm square. I hope it is clear. I hope I am clear. Now I want to maximize the margin, and see, minimizing this is maximizing the margin. Minimizing this is okay, minimizing the misclassifications. But could you clearly see one thing? If I maximize the margin, let's suppose is yellow line is my margin. Let's consider, guys, and this orange light pink color. This is my margin. I will consider these two as my margin lines, yellow and the light pink. Now see, with respect to this yellow, all the blue points are misclassified, right? Means if I increase the margin, the number of misclassifications are becoming more. Means they are reciprocate to each other. Oh, Jane, I got. Did you really got, guys? Please mention in the comment section. You can see this positive plan. All these blue points are misclassified according to this blue line, yellow line, right? Means when we increase the margin, misclassifications are becoming more. Now let's see. To minimize the misclassification, what we have to do? Our margin should be less, right? Then means there is a trade-off. If you want to increase the margin, the number of misclassifications are becoming more. If you want to decrease the misclassification, then we have to decrease the margin. There is a trade-off. That is the beauty of this mathematical formulation. At the same time we have to maximize the margin, at the same time we have to minimize the misclassification. I hope I am clear, guys. This is the beauty of this mathematical formulation, subjected to these constraints. You might be wondering what is Cj. C is the hyperparameter that would be in the hands of the data scientist, right? We can control, we have the control, yes, we have the control of whether misclassification should be more or less according to the data set. C would be calculated using cross validation across the training data, And yeah, in general we use c equal to 1 because guys, we are giving equal contribution for misclassification, at the same time the margin, right? This is the beauty of this primal problem. This is the primary formulation that we have done. And we also call it constraint optimization problem. We want to find the value of w and zetas such that these constraints would be satisfied and this formulation would be minimized, right? This is a constraint optimization primal problem. Now who will help us to do a solve a constraint optimization problem? Of course Lagrangian will come, and he says, I'll explain all those in those videos, in those 3 videos. This is the Lagrange formulation. I clearly explained there. Go and watch very clearly. Those are clearly mentioned there. And how we will find the Lagrangian solution? Gradient equal to 0 means the derivatives with respect to the independent variables we have to do 0. Okay, I got it, Jane. Then let's define the SVM Lagrangian function. F of x is this is our f of x. See my laser cursor, guys. Don't confuse, right? This is our f of x. That's what we have defined. See, this is our f of x. And these two are our constraints. This is one constraint and this is another constraint, right? These two are our constraints. Now, for each constraint we define a Lagrange multiplier, as you can see, but we have 2 constraints. That's why this is alpha I is one constraint, but we define m alpha i's, guys. Why? Because we have m constraints. M constraints we have because m data points we have. For each data point we have to define Lagrange multiplier. And similar way, beta I is a second constraint Lagrange multiplier for the second constraint zeta I. I hope this is clear, guys. This is completely clear. But there is a problem with the constraint. But there is no problem. That is not the problem of the inequality. But there is a problem that we want to think in a way that Lagrange multipliers is applicable for the equality constraint. The optimal solution that you get on solving this formulation would not be optimal because we have a inequality constraint that you can see here, right? Hope I am very clear, right? And since it is inequality constraint, we have to satisfy other conditions known as Kirsch-Tucker conditions. What are these? Let's understand. And I'm telling you one thing, to sum up, if the solution satisfies the KKT conditions, guys, if it satisfies the KKT conditions, we are guaranteed that those are optimal. We are guaranteed. How you are so guaranteed, Jane? Because they are generalized it in such a way for different problems. Yeah, that would be there. That is present in the literature, guys. Those cannot become as simple as we think. No, those are generalized and we are reading it, right? Now let's see what is the first condition, stationary condition. Everyone knows this, right? Stationary condition nothing but we have to make the derivative of the independent variables to 0. What are the independent variables we have? W, B, alpha, right? These 3 are independent variables. Let's make them 0. What is the problem here? Now you can see I am making the dou L by dou W. See, I am doing the derivative of our Lagrangian function. See, you can clearly see this is our Lagrangian function, right? Here Lagrangian function. I am doing the derivative of it with respect to W. See, if I do derivative with respect, this will become 2 by norm of W, and this is this, and here W is there, and this will become 1, and alpha I, y I, x I would be remaining from here, right? Remaining from here, and this part alpha I into b I will be 0 because no W is there. Here also it will be 0. This is also will be 0, and we end up W as this. Please pause the video here and see this calculation. This is my humble request, right? Or else you take the notebook and understand. I will give complete notes. My portfolio would be there. All the notes of machine learning would be there. Go there and understand things and explore and ask questions, right? You can clearly see this is we end up with W like this, right? Now yes, this is our we ended up with dou L by dou B. Just do the calculation, guys. Now with respect to B, this would be 0, right? Because B term is not there here, and only B term there here means alpha I, y I would be remaining. This would be 0, this would be 0. That's why we ended up with B like this. Dou L by dou B equal to 0. Oh, this is our second result. Keep these results in your mind, guys. And with respect to zeta I, you do similarly C minus alpha I into beta I. Take the notebook, write and do this, guys. This is your homework, right? Now what is the What is the next condition? This is the primal condition or primary optimization constraint problem we have defined, right? This is the primal condition. This is the constraint. This is another condition. It says, KKT says, the solution should satisfy this constraint as well. Of course, KKT, those will satisfy. And then now dual feasibility. Now the concept of duality comes here, and he says there would be a dual problem that would be easier to solve for this primal problem, and these are the conditions for those for the dual problem, right? He says, okay, what are those? Lagrange multiplier should be greater than or equal to 0. He is saying, guys, okay, there would be a dual problem. Let's see that as well. Now this is the fourth one, complementary slackness condition. Slackness condition says, see, this condition is nothing but your Lagrange multiplier into your constraint should be 0. Lagrange multiplier constraint is equal to 0. Now if you clearly see, for a support vectors, we know this is support vector satisfy the equation of pi plus and pi minus, right guys? Now here you can see support vector satisfy this, and for support vector those are correctly, support vectors are correctly classified, of course, means those zeta would be 0, that we already know, and this value would be 1 if it is if you take the positive class of support vector. If you take negative class of support vector, it would be -1, and this would be 0. This would be 0, and we already know alpha a should be greater than or equal to 0. If both are 0, it doesn't make sense. What does it mean? For the support vectors, Lagrange multipliers are positive. I hope this is clear, guys. Remember this point. For the support vectors, Lagrange multipliers are positive. Now let's substitute our 2 and 3. No, not 2 and 3. 1 and 2. 1 and 2 in this function. In this. Not this. In this. In our Lagrangian function. Let's substitute those 1 and 2 in this Lagrangian function, right? If I substitute those, I am taking w alpha a y x, right? And another term I am taking alpha j y j x j, because I could see a dot product here. If I take y a x I same both sides, I could not infer this, right? For the clarity of thought, we are just writing in different notation, and c is alpha a plus beta a, that we know, that is the third result, and that I substituted here, and zeta I minus alpha I into, and w transpose, again I have written w value here. C is my cursor. This is a simple calculation. Take your notebook and just do that, guys. Please do this. Now minus b into this term, alpha I into ya, right? Alpha I into, you can see my laser cursor. This would be 0, right? Of course, this is the second result. This should be 0, and -1. If I multiply alpha with -1, yeah, this is how we end up, because minus is equal to plus, and here minus zeta alpha, yeah, and this, it is clear, I hope, and the calculation is also very clear, yeah, and this would be cancelled, I hope, and this is our final equation that we ended up with only alpha. You can clearly see, right? We can end up only with alpha, means we don't have independent variables now. 3 variables now. We are only having alpha. Okay, Jayan. And we have dual variables, right? Dual conditions we have. We know from the third result that c minus alpha is equal to beta a, because this is our third result, guys. This is our third result. Yeah, we know that. And from duality conditions, we know these two should be greater than 0. From these 3 points, we can find another, we get another constraint. This is our constraint, 0 alpha I and less than or equal to c. This is our constraint, guys. How we got? Using these 3. This is a duality condition, and dual problem is defined like this, guys. This is what we ended up, and this is the duality condition we ended up, and yeah, this is our constraint, and this is our second result. This is our second result. Why we are maximizing alpha? Because the condition itself says alpha I will be greater than 0, but how much? That's what we are maximizing it. But the concept is way beyond this, because the duality principle is there. How primal function would be, solving primal will be equal to dual problems. Latter conditions should be satisfied, and convex optimization would be involved here. Our SVM problem is a convex optimization problem. There is a lot of depth again here, but I given a simple explanation to understand. Right, this is our mathematical formulation we ended up. We want to maximize alpha subjected to these constraints, but how we will find? Now this is an optimization problem. Remember, guys, in machine learning, First we formulate our theory as a mathematics, then we will end up with a optimization problem. Then we use optimization algorithms. Like SMO is a sequential minimum algorithm. This would fix two Lagrange multipliers at a time, and it will maximize this function, and it will fix those two, and it will take another two data points and it will consider another two Lagrange multipliers for two different data points, and these four would be considered for maximization of this, and these four would be fixed, and another two. Like this, sequentially it will find the all Lagrange multipliers, right? Okay, James, we got Lagrange multipliers as well using SMO. I will explain SMO in later videos. In some or other day I will explain this as well. Then we compute W, right? This is W, alpha I, y I, x I. Then what else we need, guys? We need only B. But to know B, let's understand. But see, before we understood slack variable is not what slack variable did. Slack variable did it made our constraint soften for every problem, right? Now we just updated the slack variable. This is our slack variable, right? This is how the slack variable is defined, right? Here W transpose, I just written what is W that we got, right? We got W as this, right? I just written that. This is our reformulation of slack variable. I hope I am very clear, guys. If you have any doubts, please mention in the comment section. And you can see here how to compute B. This is how we compute B. You can see this is our constant, right? This is our constant. Okay. For support vectors, this would be constant. Yeah, this will become inequality sign because support vectors lie on the marginal planes, and I multiply yi on both sides because yi is nothing but plus or minus 1, right? If I square, minus 1 would become plus 1, means yi square is always plus 1. That I know very clearly. Okay, Jane. Then we got B as like this. We know zeta is using this formulation for every data point, and we know. And how we will know support vector, Jane? How the computer knows those points are there? These points are support vectors. Before we got one result, before we found Lagrange multipliers, right? Those for support vectors, Lagrange multipliers are positive that we inferred before. By that, these we compute B. Then this is the reason why support vector missions named as support vector. This is like support vectors are very crucial to define your hyperplane. You got W and you got B. What else you need? You need nothing. Just yes, this is your y of. This is your formulation. This is the prediction, right? Cool, guys. This is yi should be great. If it is greater than 0 for a new point, yeah, it becomes to positive, guys. If it is less than 0, it becomes to negative, guys. If I take W and B, xi like this, and if I multiply, I ended up with 2. Okay, this is present as a positive. Yeah. I hope you understood prediction. Now, what is the big picture? This is very important. See me clearly. First, support vector define its goal. What is its goal? It wants a robust one. How? By maximizing margin. To maximize the margin, yeah, it found a general hyperplane margin. Then what it does? Okay, for maximizing, we ended up with a constraint. Yeah, positive point should be lying right side to the pi place negative. Yeah, we ended up with an inequality constraint. Then who helped us? Lagrangian helped us, right? For the optimization. Then Lagrangian, okay, for Lagrangian we have a limitation. Yeah, those would be optimal if the constraint is equality. But if it is not equality, KKT condition should be satisfied. Oh, the KKT conditions are satisfied, means those would be optimal. But again we formulated dual. Why? Because solving two Lagrange multipliers, we got 4 cases. In the last 3 videos, you go there and check in the last video, we got 4 cases there. We have m Lagrange multipliers here. How tedious it would be to solve manually. That's why we defined dual, so that we use the optimization algorithm. I hope you understood the complete picture. If a new data set is given, first Lagrange multipliers would be found using the optimization. Then we find the support vectors, we find the slack variables, then we get W, summation alpha I, yi. Hope you can see alpha I, yi, right? Then we find this, then we get this, right? Then we get B. That's it. That's how the support vector missions work, guys. Thanks for listening. If you got any value, please share, like and subscribe. Jai Hind. And these are the references. Sorry for not saying. These are see, this is very good book. Very good book is this one, the first one, and these are the in-depth mathematics books. And third one is the convex optimization book by Stephen Boyd by Stanford professor. And this is a Taylor book, is a very in-depth support vector missions depth book. And yeah, these are the references. Thanks for listening.